Good morning, everyone. My name is Laurent Solga, and I will present my team's work entitled Robotic Arm Controlled by Android App through Bluetooth Connection for Organic Solar Cell Manipulation. During this presentation, I will underline a few points: the motivation of our work, the system design, the implementation, the Android app, the final product, the conclusions, and a few things about me. I will start out with our motivation to create this robotic arm. First of all, the solar cells in the labs, in the lab facilities, when they are developed for the first time using different chemical compounds, organic materials, they are tested out on a small piece of glasses or PET flexible materials. These organic materials are deposited on these substrates, and after that introduced in different chambers for electrode depositions. The handling of this type of substrates, it's very hard when we are trying to manipulate them with the tweezers, because a small mistake, human mistake, can scratch the surface and organic cells cannot be used anymore. Because of this, we wanted to create a robotic arm to automatically handle and exactly precisely handle these small substrates. More than that, to be handled in different small areas like a glove box, and because of this, we need a remote control of them. So we need a special dedicated application. So starting out with these motivation points, we proposed our system device. The block diagram as presented in this picture, it exposed the whole operation of the robotic arm. The user can enter the manipulation data in the mobile application, which is transmitted via Bluetooth to the Atemega 328 microcontroller. The microcontroller is incorporated on an Arduino Nano development board. The electricity needed to operate the entire system is provided by an external 5-volt power supply, which connects directly to the development board, the Arduino module, the servo motors, and the vacuum pump. With the facilities given by the microcontroller, the data transmitted by the user to the application is interpreted and transmitted to the robotic arm. Based on the block diagram, we started out the design of the electronics needed to control the robotic arm. The schematic of the entire electronic system was implemented in EagleCAD and presented in the top picture. To have a complex control on the robotic arm, we considered 4 servo motors, one for the horizontal movement, which acts as a waist servo, and 3 for the vertical movements to mimic a human hand as shoulder, elbow, and wrist servo. For a finger-style action of the robotic arm, a vacuum pump was considered. Knowing that the glass probes are weighing a few grams, we choose a small vacuum pump which works with a voltage of only 5 volts. Since it has only 2 connectors, we decided to control it via bipolar NPN transistor. The entire circuit is powered up using a jack connector and a power supply that is connected to a wall outlet. The power supply provides a voltage of 5 volts and the current capability of 4 amps, mainly because the servo motors need a higher startup current. The PCB level implementation was conducted and can be seen in the bottom picture. The design of the robotic arm was done in the SolidWorks CAD. The robot has been designed to be easy to implement and use and maintain. Inside the base of the robot, as can be seen on the left side in the left picture, this base acts as an enclosure for the electronic parts for the PCB. Along the two arms of the robot, a channel was created through which the wires from the servo motors and the tube for the suction cup can be pulled. The channel starts from the vacuum pump. The use of this type of channels reduces the risk of damage of the wires when the robotic arm is in use, in action. At the same time, it gives a more compact appearance to the whole setup. If we have to split the parts of the robot, we can say that we have 6 important parts. The first one, the electronic enclosure, which will be attached to the work surface to provide stability and contains the servo motor, the vacuum pump, and the PCB. The second one, the lid, which can be easily removed to access the electronic components inside the enclosure. The third one, the rotating base on which the rest of the assembly is attached. The rotating base is mounted on a servo motor that could rotate between 0 and 180 degrees. The fourth and fifth components, they are almost identical parts, have the role of the arm and of the forearm. And the last part, the tip, to attach the suction cup with which the organic solar cells will be manipulated. All these parts were 3D printed in PETG material, which gives a high robustness to the robot. In the first phase, the user reaches, from the application point of view, in the first phase, the user reaches a home page where he sees a brief description of the functionality of the application and has the option to go further into the app. The first page can be seen on the right picture on this slide. Subsequently, the application checks whether the Bluetooth is activated on the device that is in use. If it is turned off, the user is asked if he wants to turn it on. When the connection between the two devices is successful, the application reaches the main screen. From here, the robotic arm can be controlled using the buttons that we can see on the picture. The buttons are placed next to each robot joint so that the application can be used intuitively by anyone. Under each set of buttons, there is also a label with the name of a servo motor operated by the respective buttons. More than that, we created a side menu on the main screen of the application, which is accessed using the buttons next to the page name. When it is pressed, the user can see additional functions of the application, as the disconnect button is used when the user of the robotic arm wants to end its activity. It's important when pressing this button, the robotic arm moves to a neutral position and the connection will stop. So we have a homing position for the robotic arm. And another side menu is the About and Help buttons in the info section, which gives the user the opportunity to learn about the application, either about its role and functionality or about how to use it. From the experimental point of view, we used the robotic arm in a real environment, using it to access a matrix of six organic solar cells on a thin layer of glass, as can be seen in the final product, where we have a substrate and we have 6 plates of glass, each containing 2 organic solar cells, before introducing this in another chamber to be further processed. We can say that the product it's acting very well. It's very easy to work with. Other points in the conclusion side, it is very important to handle the organic soil cells in the lab with the automated system like this, because we reduce a lot the scratching of the organic soil cells material. A proper functioning, we can see that the proper function cannot go further without a good application. So in our case, we implemented an application which can handle straightforward all the joints of the robot and mimic very well the human hand. Thank you very much for your attention, and before ending, a few things about me. I'm a lecturer at the Technical University of Cluj-Napoca, Romania. My main field of research is optoelectronic applications, organic solar cells, and fiber optic sensors. For those who are interested in these areas, please feel free to contact me, and we can develop the new products and the new great applications together. Thank you very much once again, and I wait for your questions. Thank you.